This video assumes that you have watched the video on the syntax of propositional logic. If you have not yet done so, be sure to check it out now before continuing. So remember how syntax referred to how we must write propositional logic. Then one might also wonder, okay, but what is actually the meaning of the formulas that we write? And this meaning is called semantics. So to say that the mathematical argument, so a proof, is correct, or also called sound, requires an understanding of the meaning of formulas and the relations. They're so-called semantics. And there is not a certain fixed type of semantics. We can have a different meaning for propositional logic depending on the context. So for example, in this case, we will focus on prototypical semantics, so Boolean truth values and truth tables, so true or false, two possible values. However, consider working with hardware circuits, where there might be noise that results in signals becoming disturbed, for example. Then we might also have like a third value, so true, false, and don't know, simply because we can no longer derive what the signal used to be. So we also refer to that as Boolean semantics. When considering Boolean semantics, a propositional formula can be true or false, which we will write as 0 or 1 respectively. So then remember that we started with some propositions which we turned into propositional variables. And then the question is, are those propositional variables true or false from the beginning? Because we could, for example, say, well, we have this proposition P, but actually that proposition does not hold from the beginning. So how do we denote that? Well, we use a so-called valuation function for this. Evaluation is a function phi that assigns every atomic proposition a true value. So as an example, say we take this P, we put it into the valuation function phi, and then we get a true value, its initial true value. So say P is false from the beginning, then we assign that a 0 for false. And another clear example is the absurdity connective. So in Boolean propositional semantics, we assume that the valuation of bottom is equal to 0, false. And it makes sense, right? Because absurdity never holds. So remember from the beginning of the video that I mentioned that connectives had a certain intuitive meaning. Now that we have fixed the meaning, we have fixed the semantics, we can look at this meaning in a more formal manner. So notice that for all of the connectives in this table, the arity is at most 2. So to see how all of these compound propositions behave, we need at least 2 propositional variables. And we also need to check all the possible valuations for these 2 variables. And remember that a variable in Boolean semantics can be true or false, so there are 2 possibilities. So in total we have 4 rows, we have 4 combinations of valuations to test for. So in an example, the first row of the table represents the valuation of P to be 0 and the valuation of Q to be 0. Whereas, for example, in the third row, the valuation of P is equal to 1, the valuation of Q is equal to 0. So now knowing this, we can also look at the valuations or the results of these compound propositions. And let's go over some easy ones first. So remember absurdity, and that it has an arity of 0. So it is independent of both P and Q. Remember from the intuitive meaning that it never holds. So in Boolean semantics, never holding simply means it's false. And also remember that truth is the negation of absurdity, so it always holds, so it's always true. We can also look at the negation of P as another easy one because it's independent of Q. And it simply flips the value from false to true and from true to false based on the definition of negation. So P being 0 in the first 2 rows means that the negation of P becomes 1. Whereas in the bottom 2 rows, P being true becomes the negation, results in the negation of P to become 0. Then let's go over disjunction, conjunction, and implication. So remember from the intuitive meaning of conjunction that it holds when P and Q both individually hold. So it's true when both P and Q are true. So that's only the case for the bottom row. The disjunction was true when either or both of P and Q were holding, so were true in this case. So looking again at the beginning two columns of the table and doing this row by row, they are both false in the first row, so the compound proposition is also false. And from there on, there's at least always one true, so the disjunction is also true. Then we have the if P, then Q, so the implication. So if P holds, then Q holds. Okay, so looking at the final row, if P is true, then Q is true. That seems to make sense. And then also the third row, if P is true, then Q is false. Yeah, that's not in line with the definition of implication, so that's false. Then we also have the top two cases. So remember, if P is true, then Q is true. We don't make any statement about what Q is when P is false. So Q may be anything when P is false. So these top two cases are both true. Then finally, remember the definition of by implication to be P implies Q and Q implies P. Hopefully it's a little clear from this definition that both P and Q need to be equal. For example, if they are both false, then remember from implication, we don't make any statement at all. If P is true, then Q is true. If Q is true, then P is true. If they're both false, it's completely fine to us, according to the definition. So yeah, that's one. Then remember, if both are true, if P is true, then Q is true. If Q is true, then P is true. So if both are true, then yeah, that's also completely fine according to the definition. Then finally, we can look at the two middle rows. We can realize that if P is false, so we're now looking at this second row. If P is false, then Q is true. So if P is false, then Q is true. Yeah, that's fine for that implication. However, if Q is true and P is false, yeah, that's not correct. So no, that's 0. And of course, the third row works in exactly the same way, but then this implication is incorrect and this one is correct or holds. So the by implication forces P and Q to be the same value. Now we can look at this in a more formal level, and I will very briefly discuss this. But considering we are working with zeros and ones, we can also define the result of, for example, conjunction using a mathematical function. So we can write it as the conjunction of, for example, P and Q is equal to the minimum of the values of P and Q. This makes sense, right? If one of P and Q is 0, then the conjunction also is 0. If both P and Q are 1, then the minimum is 1. Then the conjunction of P and Q is also 1. We can define the disjunction in the same manner. For example, P or Q is equal to the maximum of P and Q. Because if either of them is true, then the maximum will be 1. And if both are true, then the maximum is also 1. If neither are true, the maximum is 0. And that's also the correct result then for the disjunction connective. So that's something to consider, but that's a bit more formal and a bit more advanced. So yeah, don't care about it too much. So now finally we are nearing the end. We're going to bring everything together. So we are going to take this statement, bring it into propositional logic, and see whether the relation is valid or not. So remember from before, if it rains and Socrates has no umbrella, then he gets wet. So it's the if-then construction again. He gets wet, we denote it using W from before. He has no umbrella, we denote it using U from before. It rains, we denote it using R, and the connective end is the conjunction. So this first sentence, this first statement is, let's note it here, R and U implies W. That's the first one. Then the second sentence, Socrates has no umbrella and he does not get wet. So the second sentence then is Socrates has no umbrella. We saw that before. That's you. And is the conjunction. He does not get wet. Remember that getting wet is W, so not get wet is the negation. That's the second statement. Therefore, it does not rain. So let's just write this down as therefore, and it does not rain. Remember, it rains is R, does not rain is the negation, so not R. So how we can now more formally write this down as a single propositional formula, let's say it's called phi, is to consider the first part. So R and U implies W. That's something we assume to hold because that's a fact that was given. We also assume to hold that U and not W. And therefore, if both holds, then it does not rain, so not R. So this is the full propositional formula of what is defined here. Okay, so this is very cool. So at least I think it's very cool. So now let's make a truth table for this. So let's write it down again here. So phi is equal to R and U implies W and U and not W implies not R. So notice how we have 3 propositional variables and all 3 propositional variables can be true or false. So we get 8 rows in this truth table. This might also help you realize that truth tables, doing this by hand, can become really cumbersome for 4, 5 or more propositional variables. So the way we're going to approach the issue, because it's a really long formula, is we're going to divide it into smaller formulas to consider first. So let's look at R and U implies W first. So remember from implication that if the left-hand side is 0, it does not matter what the right-hand side is. It will always hold. So this allows us to very easily see, for example, in the first row, not both R and U holds. So the left-hand side will be 0, so the result of the implication will be 1. Here it will be 1, here it will be 1, here it will be 1, it will be 1, it will be 1. And we have 2 cases where the left-hand side will actually be true. So it matters that we need to consider W. So W must be true for the implication to hold. In this case, W is false. So here the implication is false. Here W is true, so the implication is also true. Now let's consider this to be A. So this part of the formula has become A. Now let's look at the second part. So U and not W. So again, let's make life easier for ourselves. For the conjunction to hold, both need to individually hold. In the first 4 rows, U is false, so the conjunction will also be false in the first 4 rows. Now in the final 4 rows, U is actually true, so now we need to consider W, and the conjunction is true if W is false. So here W is false, so it's true. Here W is true, so the conjunction is false. Then finally, let's look at the final bit, the negation of R. So it's simply taking R and flipping it around, right? That's the definition of the negation. So we get 1, 0, 1, 0, 1, 0, 1, 0. Let's define this as B. So this has become B, and this as C. So then phi has actually become, let's write this here. Phi has become A and B implies C. So now we can look at this final column and use these predefined parts, these predefined values, to make our lives more easier. So if the left-hand side doesn't hold, it doesn't matter what C is. So if not A and B are both true, then phi is immediately true without having to look at C. So we can very easily do this. So again, we can look at the first value A in this case, value B in this case. And we know that not both are true, so phi will always be true. And we can do this for the other rows as well. So there's only one case, one row where both A and B are true. Now we need to see whether C is actually also true for the implication to hold. In this case, yes, C is true. So the result of phi is also that it's true. So phi is always true. Phi always holds, independent of the valuation of U, W, and R. Okay, so what does that tell us? So a propositional formula is valid, or called a tautology, when it is 1 for all combinations of valuations of its propositional variables. So like we saw before, phi is always true, so therefore this is called a tautology, or the formula phi is valid. A propositional formula is satisfiable when it is 1 for some combination of valuations of its propositional variables. So phi is also satisfiable because it is 1 for some combination, but it is also valid, or called a tautology, because it is 1 for all. So it's both satisfiable and valid or tautology. Now, if a formula is satisfiable but not valid, it is said to be contingent. Okay, that's all for this video. So hopefully this clears up any doubts you might have had about propositional logic, or it taught you something completely new. So what's next in this case? Well, propositional logic can be defined more formally. So these are a bit more advanced topics, but if you want to look them up on your own, we can define propositional logic using a context-free grammar. We could, for example, also use proper semantical notation to define the Boolean semantics for propositional logic in a more formal manner. And of course, as I said, propositional logic is a rather simple logic. So if we want to have stronger expressibility for certain mathematical statements, we need to go to a higher order logic, for example, first order logic. And this will be something that will be covered in this channel at a later time. And hopefully till the next video.